So welcome back to Adventures in Science. This is video number 2. And so the first thing I wanted to show my drawing of what would happen if you did a fair test of no fertilizer versus fertilizer. So after 3 months, both of these plants are going to grow. Now notice I put them in the same ground, so they're in the same soil. If they're the outside, they would have received the same water. So same soil, same water, same sunlight. So, and I used the same kind of plant. I just picked a grass, some sort of tall grass plant. So if everything's the same, but I added the proper amount of fertilizer to this and no fertilizer here, after a couple of months, I would expect this one to grow more than this one. So now we're going to move on to our first science specific topic. We are going to look at the planets. So we have 8 planets around our sun. The sun is really big. And compared to the planets, the sun is huge. The planets are really small. So I've included this file. Maybe your parents can download it, print it out. But just in case they can't. So I have all 8 planets here in the order they would be from the sun. Now really, the 4 top ones should be over here to the left, but they don't fit on my camera. So I want you to notice how tiny Mercury is. Mercury is the closest to the sun, then Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So the first 4 planets, including Earth, are small, rocky planets. They're really tiny. They're actually pretty close to the sun. The 4 outer planets are gas giants. They are huge. Especially look at the difference between, well, look at Earth compared to Jupiter. Notice how many Earths could fit just across Jupiter. That's just, it's crazy how much bigger Jupiter is. And then also, there we're comparing the largest and the smallest. So Jupiter is huge compared to little tiny Mercury. So we have the 4 rocky planets, the 4 inner rocky planets, the 4 outer gas giants. Jupiter, by the way, if it had a bit more mass, maybe say about double the mass, actually could be a star. But it's not massive enough to be a star. But there's no surface for you to walk on in Jupiter. If you were ever to give people ever go there, they can't walk on Jupiter or Saturn or Uranus or Neptune because they're gas giants. Other things that are interesting about the planets: Earth has an atmosphere, as you know, you breathe air. Mars does have an atmosphere, but it's very thin. It is not enough that people could just walk on the surface without wearing a spacesuit. Venus has too thick of an atmosphere. It's also very hot and it's full of gases that are not good for us. So if we could go visit there, we would have to wear a spacesuit for the opposite reason: too much pressure. Mercury does not have an atmosphere. One of the interesting things about Mercury not having an atmosphere is that means that the temperature extremes are huge. It's very hot on the sun side and it's very cold. Like we're talking boiling water, freezing water easily, plus a lot of other very common things in our solar system. And then the gas giants, if we ever go visit them as people, we'll go hang out on their moons. They each have multiple moons. Jupiter and Saturn, I think, each have over 20, maybe even 50. It gets down to some definitions. And so this is how the planets compare to each other in size. Next, we're going to look at how far apart they are from each other and from the sun, but we're going to have to go outside to do that. Hi campers, we're on the sun. It is really hot here. Let's not stay here. So I took 2 steps back from the camera. So I equivalently just went to Mercury, the closest planet to the sun. So remember the pictures we just looked at? The sun on that scale would be 2.2 meters across, which is basically how big my hands are. So that's how big the sun would be. And remember, Mercury was this little tiny circle. So, but I'm now at the correct distance that Mercury is from the sun. Then, now I'm at the distance that Venus orbits the sun. Now I'm at the distance of Earth. Hi, home planet Earth, good to see you. But we're gonna keep going. So here's Mars. That's the 4th of the rocky planets. Now gas giants. They're a lot bigger and a lot farther out. Now we're going to do our second topic in science. I wish that I could have sent all of you all these materials, but a lot of you aren't going to have them around your house. And so this is just going to be one I'm going to demonstrate for you. So this is a lantern battery. It is pretty big. You use it in lanterns, like when you go camping, you might have that particular one. But it's not a special battery. It's actually just like D cells, just 4 of them put together, because this is a 1.5 volt battery, and then this is a 6 volt battery. 1.5 times 4 is 6. So 6 volt battery. And what's really nice about this, as opposed to this, is it has these 2 terminals, and it's much easier to get to them. So then I also have a bunch of Christmas tree lights. So I use these with my high school physics students in order for them to make circuits to see how this works, and it's a lot of fun because they're very inexpensive, and if something happens to them, that's okay. But it's also really easy to attach them. So if I connect one here, you can see I completed the circuit. I went from which one's the positive? I went from the positive terminal and then the negative terminal. So electricity flows through the light bulb. If I disconnect it, it doesn't work. A circuit has to have a complete path. So instead of doing that every time, I'm actually going to clip some wires on here. The colors of the wires does not matter. Wires work both ways. But you can see, again, if I complete the circuit, the light bulb lights. If I disconnect it, the light bulb turns off. I can even put a switch in the circuit. So a switch, move this out of the way for just a second. A switch has an air gap in it. I'm going to connect this for the battery here and another wire to the other side of the light bulb and this part of the switch to make sure the light bulb, everything's on the screen. So this circuit doesn't work even though everything's connected because there's a gap here. Now, if I close the switch, I've closed the gap, and now electricity can flow through the switch. This switch is loose, that's why I'm having to pinch it closed. So electricity can flow through the switch and simultaneously through the whole circuit. And we get a nice blue light bulb on again. So if you don't have a closed path, it doesn't work. If you do have a closed path, it does work, and that's true of all. Now this switch, by the way, is exactly like what's in the switch in your house. When the lights are off, you need this for there to be a break in the circuit. So it would actually be oriented like this. So this is with the switch in the down position, the off position. When you want to turn the lights on, you move it to the up position, which completes the circuit. It closes the air gap. So the next thing we want to look at about circuits is there are different ways to connect things. I can put a couple of bulbs together in series or in parallel. So remember how bright this one light bulb is all by itself. I'm going to connect just by twisting the metal, as long as you connect conductors, and metal's an excellent conductor. And now I have 3. So except they're not connected, make a plan. Do you think it's going to be brighter, the same brightness, or less bright? 1, 2, 3. And in series, it's a lot less bright. That's because the same push, the same voltage from this battery now has to push through 3 in a row resistances. There's a lot more resistance in this circuit to current flow, and so there's less current. And we see that with less brightness. And the reason this is called series is a series, like in math class, is one after another, a list. And here the current has to flow through the blue one, then the first red one, then the second red one, and back to the battery. So in series, it's harder for the current to get through because it has to do one obstacle after another. This is like an obstacle course. There's a different way to connect. And so I'm going to take these and I'm going to connect both sides together. And I'm going to do it with the same thing with the third one. Both sides together. That is getting really short. There we go. And then I'm going to in a moment connect here. So this is what's called a parallel circuit, because when current gets here, it gets to choose, do I want to go through that light bulb, or the middle light bulb, or the other light bulb? And because it gets to choose, this is actually a much easier circuit. So now when we connect it, look, they're nice and bright again. In fact, their brightness is about the same with just one connected to here. And that tells us then that there's a lot more current coming out of the battery now. Because if one is lit up in a pattern like this, just like one by itself, then there must be enough current to run this one, and to run this one, and to run this one. So there's a whole lot more current coming out of this battery. Another way of saying that is, yes, we get more light here, but we're going to drain the battery faster, because the chemical reactions that are producing that current, well, when you run out of reactants, no more. We're going to do chemical reactions here in a couple minutes. So that's light bulbs in parallel. And then I have one more thing to show you. Let me get all this stuff out of the way. So this is a circuit called, it's a kit called a snap circuit. And so in this circuit, I have, notice I've got 4 batteries. So this is actually a 6-volt circuit, just like the other one. And then the current comes through this switch, and then it gets here and it chooses. Current gets to choose, and this is a parallel, so this is a parallel path. And I have 2 LEDs, light emitting diodes. It's a different way to produce light. This is a variable resistor, and right now there's low resistance going through this side, so there's lots of current. It lights up the LED. If I switch this to the other side, the other one lights up, because now there's too much resistance too much resistance in this path, and so not enough current. This one has less resistance, so more current. And sometimes I can get it just right to get the middle to light up. Nope, not today. So depending on which path has more resistance, the more resistance, the less current, so it doesn't light up. But notice it continues. It doesn't just stop there. It has to go all the way back to the batteries, because a circuit, the current has to keep going. If there's a break anywhere, like all the way over here, it turns off. So that's electrical circuits. So this is a website I found that y'all might be interested, that you can do some circuits on the computer. So once you go to this BrainPop website, and the link will be in the supplementary materials, we're going to click Play Game. And then it's not really a game, it's a simulation. This is a really cool, I use this actually a decent amount in high school. So whether you click Intro or Lab doesn't matter, it takes you to the same place. And now you can build a circuit. So you can start by building a simple circuit. So let's do a battery. We want to light up the light bulb. Now you know we have to make a complete circuit. So if we put one wire there, connect the other one there, maybe we'll pull this down here. And then we'll take the other wire, and yay, we lit up the light bulb. Okay, so that's cool. But let's do some other stuff with it. So I want to disconnect this. So actually, I'm going to clear the whole screen. So if I scroll down here and hit reset, you notice everything's gone. So I'm going to do it again, but I'm going to do it slightly differently. So battery, let's put the bulb over here, wire to connect them. And then I'm going to use 2 wires and leave them not connected. And I'm going to do this because I want to see what conducts electricity. Conductors conduct electricity, insulators do not. And there are actually quite a few of them here. So if you scroll down to this next section, you can see there's a dollar bill. Does a dollar bill conduct electricity? Let's find out. No, it doesn't. The light bulb doesn't work. So let's delete the dollar bill. And then what about a paperclip? A paperclip does, because a paperclip is made of metal. Almost all metals are great conductors of electricity. So I'm going to delete that. Actually, before I delete that, notice something. See the really little negative blue? These are a model of the electrons. There are actually many, many, many more electrons. But when the circuit is complete, so you can see the light bulb is on, it's because the electrons are flowing everywhere in the circuit. They're not just going from the battery to the light bulb. They have to go all the way down the loop. And then if I delete part of the circuit, they all freeze in place. They're still there. The electrons don't disappear. You are full of electrons on the outside of your atoms and protons and neutrons on the middle of your atoms. So everything you run into is full of protons and neutrons and electrons. And the electrons and conductors can move. So back to our conductor insulator idea, there's a coin in here. You could try. I'm not going to do it. You could do another wire, an eraser, a pencil, a hand, and a dog. So try them all. See if they work. If you have I'm sure you have batteries at home. If you can find a light bulb, maybe from a flashlight, you can make wires out of tinfoil. And you could try this in real life and go walking around your house testing things. But this website is a really fun way to do it too.